Hello. Today we shall start probability theory second class. Second class, the first thing is classical definition of probability. So what is classical definition of probability? That is the basic definition of classical definition of probability. After that, we shall study some drawbacks of classical definition. Then we shall improve this definition, and that is actually included in your next syllabus, semester 2 syllabus, or semester 4 syllabus, whatever may be. What is classical definition of probability? If in a random experiment, total number of elementary events in the sample space Bn, n is a finite number, out of which number of elementary events favorable for event E, Bm, then probability of event E, that is occurrence of event E, is denoted by Pe, denoted by Pe, is defined by the ratio m by n. That is probability E is equal to m by n. M means number of ways favorable to event divided by total number of possible ways. Clearly, probability event E lies between 0 and 1, since m lies between 0 to n. Then we start some important notations and terminology. Classical definition of probability. What is classical definition of probability? Basically, classical definition of probability is the initial concept of probability, which requires sample space should be countable and finite number of sample points. That is discussed in first class. The classical definition of probability definition is if in a random experiment, total number of elementary events in the sample space be capital N. N is a finite number, out of which number of elementary events favorable to event E be M. Then probability of event E, denoted by Pe, is defined by the ratio m by n. That is, P is equal to m by n. That is number of ways favorable to event T and total number of possible ways. Clearly, probability of event T lies between 0 and 1. What is the reason? Because m lies between 0 to n. If m is equal to 0, then probability of 0 divided by n, that is 0. And if m is equal to n, then n divided by n, that is 1. Clearly, probability lies between 0 and 1. Some important notation and terminology. One is union of two events A1, A2. What is union means? Union means represents occurrence of at least one of the two events A1, A2. That means only A1 occurs, only A2 occurs, or both A1, A2 occur. It is denoted by the symbol A1 union A2. This is the symbol. Union of two events A1, A2 represents occurrence of at least one of the two events A1, A2. At least means only A1 occurs, or only A2 occurs, or both A1, A2 occurs. It is denoted by the symbol A1 union A2. The notation is U. Second thing is intersection. Intersection of two events A1, A2 represents joint occurrence of A1, A2. That means A1, A2 both will be occur simultaneously. It is denoted by the symbol A1 intersection A2. Intersection notation is nothing but reverse of U. Third thing is complement of event A. Complement of event A represents non-occurrence of event A. That means this is event A, and the outside of the event A is the complement of event A. It is denoted by the symbol A complement A C অথবা A prime. Then fourth one is difference of event A. Difference of event A means difference of event A from event B represents occurrence of only A and non-occurrence of B. Again, difference of event A from event B represents occurrence of only A. After eliminating the favorable point of B, and this is denoted by the symbol A minus B If you consider the diagram, then this is A, this is B, this part is only A. Now operation of union, intersection and complement of events satisfy the following law. One is commutative law. Commutative law is A union B. You can write also B union A. A intersection B, you can also write B intersection A. Okay. Then associative law. A union B union C, you can write A union B union C. Or A intersection B intersection C, you can write A intersection B intersection C. That is, association is changes. After that, third, distributive law. A union B intersection C, you can write A union B intersection A union C. That is, A is distributed between B and C. A intersection B union C, A intersection B union A intersection C. This notation will be very important for solving the probability problems. Complement law. A complement, again complement is nothing but A. A union B complement is equal to A complement intersection B complement. A intersection B complement is A complement union B complement. These two is called De Morgan's law. Very, very important. Very, very important. This application is too much. Then we start theorems on probability. First theorem is addition theorem of probability. Addition theorem of probability ki if A1, A2, AM be M incompatible events. Incompatible, another name is incompatible is nothing but equivalent to exclusive events. Exclusive events, that means no two can occur simultaneously. That is already discussed in first class. If A1, A2, AM be M incompatible events, then probability A1 union A2 up to union AM is equal to probability A1 plus probability A2 dot করে probability AM. That you can write in notation style. Probability union I from 1 to M AI is equal to summation I from 1 to M probability AI. Okay. Again, I want to discuss addition theorem once again. If A1, A2, AM be M incompatible events. Incompatible, what is the meaning of incompatible? It means no two can occur simultaneously. All are separate to each other. Example, if you think one coin is, suppose one coin is tossed 2 times, then there will be 4 outcomes: HH, HT, TH, and TT. Now, out of this 4, you can get 1. These 4 never occur simultaneously. No two can occur simultaneously. Either you get both H, or you get HT, or you get TH, or you get TT. This is the concept of incompatible events. If A1, A2, AM be M incompatible events, then their union is equal to nothing but a probability A1 plus probability A2 plus. This is called addition theorem. In notation, we can write probability union I on to 1 to M. This is the notation style. Some important corollaries. Corollaries means that some derived results from the addition theorem. If A1, A2, AM be M exhaustive and incompatible events. Previously, we said they are incompatible events. Now we say they are exhaustive and incompatible events. What is the meaning of exhaustive? Exhaustive means the total sample space will be covered. Total sample space will be covered. That is the concept of exhaustive. Incompatible means no two can occur simultaneously. Then probability A1 plus probability A2 plus probability AM becomes to 1. In particular, A and A complement are 2 exhaustive and incompatible events. Okay. Then naturally probability A and probability A complement is equal to 1. So we can write probability A complement is equal to 1 minus probability A. Extended to m events, probability A1 union A2 union AM, we can write 1 minus probability A1 union A2 union AM complement. Then again 1 minus probability A complement intersection probability A2 complement by De Morgan's law. This is actually De Morgan's law application. De Morgan's law. Okay. Then second, if A1, A2 dot AM be the exhaustive forms of event A. Exhaustive forms of event A means event A can occur in these incompatible forms. Okay, I want repeat once again. If A1, A2, AM be the exhaustive forms of event A, this sentence means event A can be executed. These are A1, A2, AM concept. Then probability A1 plus probability A2 dot probability AM is equal to PA. Previously we say this is equal to 1. These are the exhaustive forms of the sample space. And next one, this is the exhaustive forms of event A. That means total is this. And even exhaustive forms of sample space probability of sample space is equal to 1. That's why I write 1. Third one is if event A implies event B. What is the meaning event A implies event B? Event A implies event B means event A is totally contained in event B. That means there is no existence out of B. That means event A implies event B. Then probability B minus A is equal to probability B minus probability A. That means the sentence implies A intersection B is equal to A. We discussed here we explain the proof also. Now event B can occur in two incompatible forms by ways, B with A and B without A. Therefore, we can write probability B is equal to probability B intersection A, probability B intersection A bar. After commutative, you can write probability A union B and probability A complement intersection B. Okay. Then by mistake I say probability A union. Second line is probability A intersection B plus probability A bar intersection B. Now probability A intersection B is nothing but probability A intersection B is nothing but probability A, because due to this, so then we can write probability B minus A is equal to probability B minus probability A. That is proved. Clear? After that, we discussed theorem 2. First one is theorem 1. First one is theorem 1. This is theorem 1, that is addition theorem. Now we discuss theorem 2. This is called generalized addition theorem. Why it is called generalized? Here A1, A2, M events, any M events. Any means there is not necessary to be mutually exclusive. Theorem 1A, we say M events are mutually exclusive. Now we say they may be exclusive, may not be exclusive. That means event A not necessarily mutually exclusive. Then probability A union A2 up to probability AM is equal to this is the formula summation I running from 1 to M probability AI. After that minus taking 2 events. After that plus taking 3 events. A dot then taking all events. This is called generalized addition theorem, or it is called Poincare's theorem. Poincare's theorem. Poincare's theorem. This is the name of the scientist. In particular, if A1, A2, AM be M incompatible events, then A1 union A2 is equal to this, because when events are incompatible, all intersections are 0. That means only this part is remains. This is called generalized addition theorem. This can be proved by the method of mathematical induction. What is the concept of mathematical induction? Mathematical induction means first we prove for 2 events, then we prove for 3 events, after that, and so on. For our MN1 or MN1 syllabus, the proof will come up to 3 events. That's why I also show the proof only for 3 events. When n is equal to 2. That means A1, A2. Events A1 can occur in two incompatible forms, A with A2, A without A2. I am interested with A1. The A1 can occur either with A or without A. Therefore, probability A is equal to probability A intersection A2 plus probability A1 intersection A2 from the previous result. Again, similar way, A2 can occur into incompatible forms, A2 with A and A2 without A. Therefore, A2 is equal to A2 with A, A2 without A. Using commutative law, we can write probability A1 intersection A2, probability A1 bar intersection A2. This is 2. From combining 1 and 2, we get probability A1 plus probability A2 is equal to probability A1 intersection A2 plus probability A1 intersection A2 bar plus probability A1 intersection A2, then plus probability A1 bar intersection A2. Last three items, you can write probability A1 union A2. Since event A1 union A2 can occur in three incompatible forms, A1 with A2, A1 without A2, A2 without A1. Okay. So instead of these three, we can write A1 union A2. Then after adjusting the site A1 union A2, we can write probability A1 plus probability A2 minus probability A1 intersection A2. This is hence the theorem holds for M is equal to 2. This is denoted by the relation A. Then we add another event when M is equal to 3, A1, A2, A3. We start probability A1 union A2 union A3. You can write A1 union A2, then union A3 in style of 2. Then applying the previous result, we get probability A1 union A2 plus probability A3 minus probability A1 union A2 intersection A3. Just apply the relation A. Then we A1 A2 remains as it is A3. This is written A1 intersection A3 union A2 intersection A3 by distributive law. Then after that, this is also union of two events. This is again union of two events. So we can apply the result A. Another, this will becomes probability A1, probability A2 minus probability A1 intersection A2. Then this is again probability A1 intersection A3. Then probability A2 intersection A3. Then probability A1 intersection A2 intersection A3. After arrange the probabilities, a probability A1 plus probability A2 plus probability A3 within one set, minus probability A1 intersection A2 minus probability A1 intersection A3 minus probability A2 intersection A3, that is kept in another set, and then probability A1, A2, A3. In compact notation, we can write in this way: one connection, first connection sign plus, then minus, then plus. Okay. Hence, theorem holds for M is equal to 3, and so on. Your syllabus is up to 3 events. Then it is okay. From general addition theorem, we also again get two important corollaries. One is probability A1 union A2 is less than probability A1 plus probability A2. This is called Boole's inequality. Boole's is the name of the scientist. What is the proof? For any two events, we get probability A1 union A2 is equal to probability A1 plus probability A2 minus probability A1 A2. This is actually relation A. This is actually from relation A. Then it is less than equal to probability A1 plus probability A2, since probability A1 intersection A2 greater than equal to 0. Probability A1 intersection A2 intersection means this side. This is either 0 or greater than 0. Here sign of equality holds when this equal to 0. That means A1 A2 incompatible. Incompatible means there is no intersection. This is the incompatible concept. Then probability A1 intersection A2, another next corollary. A1 intersection A2 greater than equal to probability A1 plus probability A2 minus 1. This is called Bonferroni's inequality. This proof also shown for any two events A1 union A2 is equal to A1 plus A2 minus probability A1 intersection A2. Next, the right hand side, we can write right hand side less than equal to 1 since A1 union A2 less than equal to 1. Then minus probability A1 intersection A2 side change after changing the side minus A1 minus A2 plus 1. Then changing the sign probability A1 intersection A2, the connecting sign will be greater than equal to probability A1 plus probability A2 minus 1. Here sign of equality holds when A1 in A1 union A2 is equal to 1, and that is events are collectively exhaustive. Next class was about one important thing I want to repeat once again, the important last two corollaries, that is one is Boole's inequality and one is Bonferroni's inequality, and very, very important for examination purpose. These two results often come in the every year, and these are very important for as the application of addition theorem. And addition theorem itself is very important. We have a plan to discuss some last year question paper, past question paper. Then you will see Boole's inequality, Bonferroni's inequality every year in the question paper, and these two results are also important for solving problems also. Okay, bye. Next class we shall discuss multiplication theorem of probability.